Welcome to a video walkthrough of the climate change simulation. The simulation gives students the opportunity to change the level of human-induced carbon dioxide emissions and then to observe how it might affect the global climate over time. The information box explains the simulation setup, which I will discuss along the way. In the last paragraph, there are questions that help guide students' understanding of processes seen in the simulation, such as, what is the relationship between carbon dioxide emissions and temperature? Here we have the simulation window. It can be moved and adjusted by clicking and dragging. The simulation runs within the CodeApp software, which is a platform where datasets can be explored in a very user-friendly way. The CodeApp functions can be found in these toolbars at the top of the browser window. There is also a CodeApp menu drop-down button here in the top left corner. I will later show you how students can analyze data generated by the simulation using CodeApp. For now, we will focus on the simulation window. A user can control the amount of carbon dioxide emissions by adjusting the human emissions scroll bar. A value of 100% indicates that human emissions are at 2010 levels. From 100%, one can decrease CO2 in 5 increments to the left to 0 emissions. Note how the power plant disappears at 0 emissions. We can increase in 5 increments to the right to double the 2010 levels. Let's see what happens when we start a simulation by clicking on Start. A number of processes occur in the image on the left with yearly time steps into the future given by this counter. The initial year is always 2024. These graphs show how climate-related properties are changing as time goes on. The top graph is a time series of global average air temperature, and the bottom graph shows concentrations of atmospheric CO2 in green, oceanic CO2 in blue, and atmospheric water vapor in black. Note that the plotted values are not actual temperatures and concentrations, which means that changes in time are relative. We can make comparisons to the initial values, for example. So let's stop the simulation to determine what these values are. I can remove the legends by clicking on Key and zoom in somewhat to be able to see better. Air temperature starts at 0 degrees Celsius in 2024. The atmospheric CO2 at 28, atmospheric water vapor at 10, and oceanic CO2 at 0. Next, I want to focus on the image. Note that one cannot continue the simulation once it's been stopped. To start a new simulation, click on New Run, which takes us back to the year 2024. The image represents the Earth with its atmosphere and clouds, its ocean and sea ice, and its land and ice sheet. The power plant is the source of human-induced CO2 emissions. Clicking on Show Key tells us what the colored dots represent. Before starting the simulation, we can see carbon dioxide molecules in green, water vapor in blue, and heat in red. The yellow and magenta arrows represent solar and infrared radiation respectively, which will become visible when the simulation is running. I want to slow down the simulation using the speed scroll bar to look at the energy dynamics more clearly. Let's remove the gases by unchecking the gases box. Solar and infrared radiation can be scattered in the atmosphere or by the land, ocean, or ice. Radiation absorbed by land, ocean, and ice surfaces turn into heat packets. Heat packets, in turn, can be transformed into infrared radiation at these surfaces. By clicking on Follow Energy Packet, it is possible to track a randomly selected energy element. You will notice that the ice sheet and sea ice will grow or shrink depending on the global air temperature. By checking only the gases box, we can see how CO2 and water vapor interact with the environment. An increase in water vapor causes an increase in clouds. Note how some of the CO2 becomes sequestered at the bottom of the ocean. By clicking on Follow CO2, one can track the path of a CO2 molecule. Earlier, I told you that it is possible for students to explore the simulated data. They will require datasets to be able to do so. That is what the Analyze Data button is for. Clicking on the button provides us with the data for that simulated instant in time when the button was clicked. I am going to click it another few times to get more data points. Let me enlarge the table and expand the columns to be able to read all the headings. So for the simulated moments in time, we have the data number under run. Here, the temperature change, air CO2 concentration, ocean CO2 concentration, atmospheric water vapor concentration. These three columns indicate whether the boxes were checked or not. Human emission rate is a number between 0 and 1, representing the value of the human emissions scroll bar. 0 for zero emissions, 0.5 for 100% emissions, and 1 for 200% emissions. The data table can be saved as a CSV file on Google Drive or on one's computer by clicking on this little ruler and then on Export Case Data. To use the data in CodeApp at a later time, the CSV file icon can be dragged into the CodeApp workspace, which I will demonstrate shortly. Alternatively, the file can be opened in Excel. Next, I would like to simulate a CO2 emission scenario to show you how a meaningful dataset can be obtained and how CodeApp can be used to investigate this data. First, I have to delete the current data entries by left-clicking on each index number and selecting Delete Case. Note that closing the table will not clear the data points that are already there. One can reload the web page to clear the data table. I'm going to reduce CO2 every 5 years from 2030, such that it becomes zero in the year 2050. I will then continue running the simulation to the year 2100 to see the state of the climate at the end of the century. I want to save my data at 5-year intervals, starting in 2025. So my first data point is saved in 2025. I will reduce CO2 with 1 increment in 2030. I also want a data point here. Next, I will reduce CO2 with 1 increment in 2035. And obtain a data point. In order to save time, I have completed a similar run before and saved the data file on my desktop. So let's stop this run. I can now drag the file icon of the previously saved data from my desktop into the CodeApp workspace. I'm going to say, create a new data set. And there is the data table. We are now ready to do some data visualization and analysis in CodeApp. Click on the graph icon to start creating a graph. We can first plot a temperature time series. To assign the horizontal and vertical axes, simply drag the headings of the desired variables into the title positions on a graph. I will drag here into the x-axis position and temperature change into the y-axis. Select connecting lines under the ruler option to turn it into a line graph. This is a smoother version of the graph one would have in the simulation window due to the larger sampling interval. If I want to add atmospheric CO2 on the same graph, it can be done on the other y-axis. We might be curious to see the correlation between these two properties. So we can create a scatter plot on a new graph. On the x-axis, I will place temperature change. And on the y-axis, air CO2 concentration. Select the ruler and least squares line. This gives us the best fit line and its equation. time series of atmospheric CO2 and oceanic CO2 on one graph. I will have here on the x-axis, air CO2 on one y-axis, and oceanic CO2 on the other y-axis. You can see that the scales of the y-axis are not the same. To make the ranges identical, click and drag on one of the axes. Note that by hovering over a data point, one is able to read its value. I recommend that you save the workspace in order not to lose plotted graphs. This can be done from the Code app menu. Saving can be done either on Google Drive, where subsequent saving will be automatic, or on one's computer. This emission scenario example and the graphs I showed you are, of course, just suggestions. Please feel free to play around with the simulation and its data in Code app. I hope that you found this video helpful and that the simulation activity will be of great value to you and your students. Thank you for watching.